Hey everyone, my name is Hugh McKee. We're in the last session, so thank you for hanging in there. You guys are the hardcore for sticking with us on this. If you were in the last Duncan's session, I'm hoping I'm not going to be too redundant, but we're going to be talking about microservices that scale and do not fail is the title of the talk. So I wanted to kind of scare the heck out of you and then pull you back maybe a little bit. But anyways, I'm a developer advocate at Lightbend. And just before coming to Lightbend, I had a really long career at HP, doing all kinds of things the wrong way. So now I'm trying to learn how to do things the right way. So in any case, I'm going to zoom through a lot of this stuff. You've probably heard this over and over the last couple of days, what's the driving motivation for going reactive? And it really kind of comes down to the customer's expectations are really high, the business wants more functionality really fast, but the big one I think here is that there's almost a tsunami of data coming at us. And I'll kind of end on that, but I think a lot of you already are experiencing this, but if you haven't, I think we're going to see this huge wave of data coming at us over the next few years. So to me, there's kind of this renaissance in system architecture that's occurring. I like to put a positive spin on things. It's like everything that we know we're having to relearn pretty much, but there's just massive changes that are occurring. It's amazing to me because I've kind of been watching technology change for a long time, and now I think it's more interesting than ever. There's the coolest things I've ever seen happen in the industry are really happening right now. And in many cases, when we start talking about modernization and so on, we start talking about the monolith. And how many people recognize this picture? All right. This picture is from one of my favorite movies, 2001. That's going to be 50 next year. I can't believe it. It's going to be 50 years old next year. It was made in 1968. And they had this awesome monolith that was a central thing of the movie. But in our case, the monolith is really composed of, I look at it from the perspective of code and data. It's not just code, but there's data involved as well. And I don't think this is justified. A lot of people are referring to the monolith as a big ball of mud. You may have heard that term. You may have heard it this week. But this is a tried and true technology. It's worked really well for us for decades, actually. And it's a well-oiled machine. And most of us grew up building monoliths, and we know how to do it, and we know how to do it really well. So I'm not here to say that monoliths are a thing of the past, and you should be screaming away from monoliths and going to the new stuff. It's just that monoliths are great, but there's new things that are starting to address some of the challenges that we're running into. And monoliths have good features like they can scale and things like that, no problem. So I'm not beating up the monolith. But one of the challenges that we've run into, this is historical forever, that you're playing this balancing game. How much hardware do you buy? How much capacity do you buy that adequately supports the system without buying too much? It's this game that you're playing all the time with the peaks and valleys of the loads that go on the system. And the horror that can happen is that you underestimate, that there's these peaks that happen where you simply don't have enough capacity. And it's not necessarily just that you don't have enough hardware capacity, it's that you've got architectural limitations in the system that can't go any faster. And that's not a good place to be. I've been in situations where you run up against a brick wall, say in a database, and everybody starts climbing on the problem. The DBAs come out of their sancted empires or whatever, and they start saying, "Oh yeah, we'll fix this problem for you." And they start tweaking and twiddling the database, and they get a little bit more, a few percent more out of it. But in many cases, we've been banging up against this. It's kind of a ceiling. That's what I'm trying to show in this graph. It's kind of this ceiling, and you just can't push it up any higher with the architecture that you're using. So it's not just that you can throw more hardware at some problems. It's sometimes you got to look at a different architecture. And it kind of really comes down to things like this, Amdahl's law, where basically all it's saying is it's got some math to prove that you can only squeeze so much blood out of a turnip. Basically, you can only push things so far before you run into things like limitations on parallelism. And there's typically choke points that we deal with. So, this picture on the left here is a bunch of sheep trying to get through a single gate. Sometimes that's the way it feels like trying to push stuff through your architecture, that you run into some kind of choke point and it just won't go any faster. And there's also the weakest link type of thing, where you've got an architecture where you're trying to minimize your risk. You want to build systems that just stay up, that don't fail. That's the whole point of this talk here. So this is the push to new things, like going to something that's a lot more distributed, has a lot more capabilities, here it's showing, I don't know where this is at. Anybody know where this is at? Because this is an interesting picture. I just found it on the internet, but it's, these tons of escalators, to increase capacity. So an approach that people are starting to use, this isn't the only approach, is you start to edge into a more distributed type of architecture. So one approach that some people use is they start carving off functionality from the monolith and re-implementing it in some form of a microservice. And they just start carving off more and more of the system to try and gradually address the, trying to get into a more distributed type of an architecture. And this is a great way to start, and a lot of people that I run into are doing the things this way. And we call it a microlith. I think you might have heard Jonas mention it, calling it a microlith, not a monolith. I don't consider that to be a derogatory term. It's a distributed monolith, which is great. You're heading in the right direction. But the key point I want to make here is that we've broken apart just one part of the equation, of the two-part equation. We've broken apart the code, but we haven't broken apart the data. Typically, it's a lot easier to break apart the code than it is to break apart the data. A lot easier. But the risk, of course, some of the risks didn't go away. We started to build a microservice system. We've carved off some of our code. We started doing microservices, but you still have the potential choke points, that hard ceiling that you can't go any faster, and you still have some single points of failure, the weakest link. So I don't know if you saw this picture, but earlier this year, this poor young lady was taking a selfie in this museum, and she hit one of these pedestals, and it caused a cascading failure of pedestals. It cost about $200,000 worth of damage. And this is kind of like sometimes you build you're trying to build a distributed system, but it still all falls down right, when something breaks. So when I talk to people about microservices, I'd like to see where people are at in their journey, and it's all over the map, and none of it's wrong. I don't want to position it in that way, but I kind of have three general questions that I ask, and three general goals for microservices. So the first one is relatively easy, that you're building microservices that are independently deployable. Like the microliths. You're carving off some of the code and you're starting to distribute it out. The next one is harder. It depends on your organization, but this one can be a big challenge. It could be like, no way, you're not going to break apart my database. It's not going to happen. And that's okay. You push it as far as you can. Maybe someday they'll wise up and you'll start to carve off. The idea, though, is that I'm on a microservice team. You're on a microservice team. You own your schema. Your team decides what your schema looks like. My team decides what my schema looks like. We've broken that coupling. If we're both using the same database, we've got to talk to each other. If I want to change a table, you might be using that same table. Now we've got to get into meetings and coordinate our releases. You've got coupling. So we're trying to reduce that coupling. And the third one is, this is a little bit easier if you've gotten over the hurdle of the data, is the only way to get to your data is through an API, through the API of the services. There's no backdooring to the data. And to show you how important some people think this is, especially this independence and loose coupling, this happened at Amazon way back in 2002. So basically, this came out from, I think it was a mandate from Jeff Bezos, and he said that from this point forward, the only way you're going to talk to your services is through an interface, through an API. No cheating, he also said, no backdoor. And he said, if you don't do it, you're fired. It's like, wow. Okay, but this is 2002, and it's worked pretty well for them, right? I mean, I was at a hardware company, HP, and the horror for me was watching a hardware company see a retailer come along and show us how to do the cloud, right? But these guys are like the leaders in how to build systems. They're not the only leaders, but they've definitely been way ahead of the game for most of us. So again, the idea is reducing that coupling. You want to build a system that's composed of services that have that independence, not only at the business level and the implementation level, but at the runtime level, so that when one of those services goes down, the system as a whole can continue to function. And this is where I want to start to get into some of the details, where it's not really just this kind of matrix of services, that in many cases when you build interesting microservice systems, you've got these interesting conversations that are going on between services. And this is really where I'm going to be diving into. So the scenario I want to walk you through is something I came across in an article written by Chris Richardson. It was a two-part article, developing transactional microservices using aggregates, event sourcing, and CQRS. You've been hearing about event sourcing and CQRS from the very beginning here. He wrote some really good articles. He's also the creator of Microservices.io. It's a really good website, a good resource. But I really found these articles interesting. So in this article, the scenario that he walked through was the exchange of interactions between a couple of microservices that are particularly interesting. So the idea here is you got an order service and a customer service. So say the order service receives a request to create an order, right? So the point I want to make here, this is a transaction. A transaction happened, the order has been created, it's a fact, it's done, right? After that transaction has created the order, some form of a message, and we won't get into the details of the actual transport, but logically, there's a message that's being delivered, say, from the order service to the customer service. The customer service, when it receives this message, looks at the request, and what it does is it tries to do a credit check on the customer. If the credit's okay, it's going to perform a second transaction. So it's going to reserve the credit, all right? And then the third thing is after that happens, then a message goes back. It could be the response or another message, but the message goes back to the order service that says that the credit was approved. This triggers a third transaction, that now the order has been changed from, say, a new order to an approved order, okay? So not every system is built this way, but I think it kind of shows the point. There's an interesting exchange of messages that are occurring, and there's 3 individual database transactions that occurred. Now, the difference is that in the monolith, this is probably done as a single transaction, right? But now we're moving into this world where all of a sudden, single transactions are decomposed into multiple transactions. And things get really interesting, because now we have these messages that are going back and forth that are coordinating transactions outside of the boundary of transactions. So we have to deal with these things. I'd like you to think about this. We're going to come back to this in just a minute, but the question is, does it matter if this is the exchange of messages, is it asynchronous or synchronous? So think about that for a few minutes and we'll come back to that. So this is the scary part, that you've got order on one side of the chasm and customer on the other side, and you've got this really scary looking bridge over this ravine where if it breaks, you die, right? But it's not that scary. It's more like this. I want to leave you with this, okay? You got this really cool modern bridge. It isn't going to break. You know how to build the bridge, and you can have a system where you can deal with these kinds of things, where you can send messages across this bridge, and you're not going to die. But a really important point is, when you're building these systems, you have to face failure dead in the face right from the very beginning. You can't think about failure after the fact. You have to think about failure right from the very beginning. So I always it's not if, it's when. It's not if a problem occurs, it's when the problem occurs. What's your system going to do about it? What will go wrong? You got to think about what will go wrong. So it's pretty obvious. So when we look at this exchange, order did some action, a message has to get over to customer, but it can't because the network's down. But it can continue. Maybe the message made it to customer, but before customer could process the message, it goes down. So the transaction wasn't completed on the customer side. Maybe customer completed the transaction, but it couldn't send the response back or the message back to order saying, hey, I did it. So from the perspective of order in this type of situation, it doesn't know what happened. All it knows is it never received any kind of response back. So these are things that you have to consider. And it keeps going on where, say, customer did its thing, and now it's trying to send a message back to order. Order got the message, but right before it completed that transaction, it died, right? So Again, it's what will go wrong. And you got to think about every possibility, because otherwise what's going to happen, because you're outside of the bounds of a nice, comfortable, solid transaction, that things could fall on the floor. These messages could be lost if you don't compensate for that. So back to the asynchronous or synchronous. A common thing that people do is we use REST, right? A synchronous REST from one service to another. That's fine. There's no problem with doing that, but the realization here is that even if you're using an implementation of a synchronous operation, this is still an asynchronous operation. And the reason is that at time one, we did an order transaction. Sometime later, we did a customer transaction. They're not connected. Doesn't matter what technology you use, they're not linked. It's not a single transaction anymore. You've got two independent transactions, which means they're happening at different points in time, which means it's an asynchronous operation, no matter what your implementation is. This is the one that scares me the most, is people use synchronous, and they think, okay, everything's cool. If I get a response back, everything was good. It is when everything's working, but it's when things break that you have a possibility of dropping messages, which can, in this case, in this scenario, that would result in orders being stuck in a new state, not an approved state, for forever until somehow it's fixed. So it's kind of, you're saying goodbye to ACID. I mean, we're not completely saying goodbye to ACID, but the all or nothing deal that we know and love so well in our monolithic systems is not the same anymore in a distributed system. And this goes even for Kafka. Kafka is absolutely wonderful for getting data from here to there. But what I was trying to show here is that Kafka is like getting on an airliner. Airliners are really safe. I even looked at the statistics. It's like, I think it was last year, less than 200 people died in airline accidents. And about 3,400 people a day die in car accidents. So it's pretty safe transportation. Kafka, if you get a message into Kafka, it's going to go from the origin to the destination. That's what it does. But it's that stairway that's risky. It's that bridge, right, that you got to deal with. It's not only getting the message from after the transaction occurred in order, getting it into Kafka. There's a gap there where you're at risk. It's also getting the message from Kafka back into customer. There's another gap where there's a risk. If you don't compensate for it, it's going to catch you. It's going to bite you. You're going to have a failure. You're going to come up from that failure. You're not going to know that these things happen until some customer comes back or the business comes back and starts wanting to rip your head off because you've dropped a few orders. You delivered successfully 1 million orders, but you dropped, say, 10. Now you're a jerk because you dropped just 10. Insignificant, but you've got this fundamental flaw in your system. I've been there. I've had systems like this that had this problem. It's not a fun place to be. So Jonas also mentioned in this talk there's different approaches for doing messaging, push and pull. So we're going to look at both. But before we get into that, there's kind of the semantics of message delivery. There's at most once, at least once, and exactly once. At most once, I kind of like to think of it as maybe once. That most of the time, messages will be delivered, but there are certain scenarios where the message will be lost. And this is the way Akka works, for example. Akka sends asynchronous messages between actors, and there are situations when messages won't get through. The next one is at least once, but this is also once or more. So that means that the message will arrive, but it might arrive more than one time. So the receiver has to deal with that. And if you were in the previous talk with Duncan, I heard him talking about the fact that you have to have some kind of idempotent type of operation where you receive the message, you got to recognize that you've seen this message before. And then there's this exactly once, which is kind of like breaking the speed of light, I think, or essentially once. And I'm not going to get into the details of that, but I know Kafka, they came out with something where they have exactly once, and that's a really interesting discussion, and they were very open about it, but we just wanted the time to get into it. How many of you are familiar with the Simian Army at Netflix? Anybody do what Netflix does? Do you actually break things in production? Not a hand, okay. I've been asking this over and over, and I've run into just a few that are doing it. If anything, I think what you should do is, when you're building systems and you're implementing them, pretend like you're working at Netflix. Because the result is that for Netflix engineers, when they they deploy code into production, they got to deal with the fact that they know that this team, this simian army team, is going to come along and deliberately break and brutalize their code, right? They're going to look for flaws in your code where there's going to be problems. That has a psychological effect on you as a developer. You know that you're going to have to pass their test. It's different, I think, than thinking about, oh yeah, we're going to throw the code in production and we hope problems won't occur, but when they do occur, we'll deal with it then. It's a form of procrastination. I think what the brilliance and the genius behind the simian army approach at Netflix is it forces everybody to think about, yeah, we have to be ready for the simian army. So pretend like you work at Netflix when you're building systems. So the big point here is that there's this non-transactional gap that you got to deal with in any form of exchange of messages between services. It's not in all cases, like if you're just retrieving information, who cares, right? But it's when one state change occurs and a message is sent and another state change occurs and these both have to happen or the system's not consistent, that's that non-transactional gap that you got to compensate for. And it doesn't matter, again, if you're pushing data from your service into Kafka. You might think that that's safe, but there's a gap there. There's a risk that you've got to deal with. So which approach to use, push versus pull? Either one is fine, but you just need to do it. So in general, the push approach is that there's some kind of queue or some kind of log of messages that need to be delivered. And there's some kind of logic that's implemented on the producer side to make sure that those messages get sent. There's retry. When things break, there's some ability for the producer of these messages to deal with the outage, and when the outage is, whatever broke is recovered, then it resumes sending the messages, and it doesn't miss any messages. Everything gets pushed through. That's one approach. Again, it doesn't matter if you're just saying, oh yeah, I just did this transaction, I'm going to make a quick call to Kafka, and it's going on to Kafka, and everything's cool. You just passed the non-transactional gap there, right? You're going to lose messages at that point. You've got to think about these things. The other approach is pull. So in a pull approach, you've got the consumer. It has some form of a reader, and it's offset driven, where you've got some kind of a log that the producer is creating of messages that were created, and the consumer is just working its way through that log. So it's just trying to keep up with some form of an offset base where it's just keeping up. So this is a form of eventual consistency where the producer of messages maybe is running really fast because it's got a high load, and the consumer can't keep up with it while there's a heavy load, but eventually it will catch up. But it works just as well when there's an outage. If the network breaks between the producer and the consumer, when things come back up, the consumer can catch up, right? It'll heal, the system self-heals. Again, Kafka is there as well. It doesn't matter if you're going all the way across between two services or you're just covering that little non-transactional gap between your transaction and Kafka, you still have to consider this. But this is exactly the way Kafka works, right? I mean, with Kafka, it's offset driven. This is why they do it this way, because pull, it's a pull approach, but they have taken this into consideration of approaches for not losing any messages. And it's really important that you consider this, the entire journey of messages going through your system. So this kind of gets into event sourcing and CQRS. You probably heard about this in other talks. I hope you did. It's a really interesting and controversial at times approach. I've had some really animated discussion with even like some of the Lightbend engineers. And they're saying, because I'm kind of pushing, I like this idea, and I'm kind of pushing it and championing it, and some of these other guys are saying, no, man, you got to slow down, back off, because there's things to consider. So there are things to consider. It is different. But this is kind of it in a nutshell. You got an event log, right? So commands come in. Those are kind of requests to have something happen in the future. That's the way I kind of look at a command. Please update, here's a deposit. Please deposit this in my bank account. Please add this item to my order. A request to do something in the future. The thing that processes these commands validates that command's okay, and it produces an event. And an event is a historical fact, something that's happened in the past, right? So commands are requests for future, events are something in the past. They go into an event log. Using this approach can be extremely fast, right? Because you got this dead simple data structure, an event log. It's like a key value type of thing. It's time-based or sequence-based. There's like an entity ID and a timestamp, or an entity ID and a sequence number, some kind of unique key. But it's not very queryable. You can't do a query against it and say, show me all the orders for customer so-and-so, for example. So this is where the command query responsibility segregation part of it comes in, the query part. There's the write side and there's the read side. So the read side is you're storing the data in a form that's convenient for query. Again, you probably heard about this before. The thing I want to focus on is, guess what? We've got a non-transactional gap between the event log, the write side, and the read side, right? Things that happen on the write side have to somehow eventually get over to the read side. So the same approach, you either have to do a push with guaranteed at least once delivery, or you have to do a pull with guaranteed at least once delivery. Otherwise, stuff's going to happen on the write side that you don't know about on the read side. And when that happens, users get mad at you, the business get mad at you, you're a jerk, right? So you have to compensate for these things. Just real quick, I want to show these. Pat Helen, Jonas, I think he had actually this quote in his keynote. I just love this guy. The way this guy thinks is just amazing. And if you ever get a chance, any paper that this guy's written, read it. It's always good stuff. But the truth is in the log. The database is a cache of a subset of the log. That cache subset happens to be the latest value of each record and index value from the log. This kind of blew my mind when I first read it and wrapped my head around it. It took me a little time to kind of internalize this. But basically, what I took away from this was that all along when we use the databases that we've known and loved and we've been using for years, we're basically kind of keeping the latest value of stuff. And we're effectively throwing away the history, right? And we grew up, we did this from an economy standpoint. We couldn't afford to keep tons of data. But now that's changing, right? Now it's a lot cheaper to store data. And it's actually kind of surprising if you contrast how much data you have to store just the current state versus keeping all the history. Orders, for example, have a very short history. A bank account has a long history, but many things have very short history. A very few number of events actually accumulate into the current state of an order, for example. But you can have that rich history. Also, really quick, I just read something about negative data. And the takeaway I had from this article on negative data was that there's things like abandoned orders. Typically, because we're only saving the current state, we're usually only saving orders that were successfully created. If you're using an event log, it's possible to have orders that were abandoned. All the things that, what the items were put into the cart, what were removed, how long was the user there, and then then they went away. That data is there to be harvested and analyzed, right? If you're keeping history. So there's interesting things going on here. The other one that blew me away was this one: accountants don't use erasers. And it was like a duh moment for me. It's like, wow, all I've done all my career is throw data away. I used erasers. Every time, CRUD, update, delete, you take your eraser out and you're throwing away data. And the point that Pat Helen was making in his paper was that that's not how accountants work. We don't throw away data. And this last one I thought was interesting as well. He actually wrote it during the SOA era, but it applies to microservices. It's moving to microservices like moving from Newton's universe to Einstein's universe. His point there was pretty interesting. The idea is that in Newton's universe, time is the same. And with transactions, one of the great things that a relational database does for us is that from the perspective of every single transaction, all other transactions either happen before it or after it. It's really interesting. I mean, databases are marvels at concurrency, but when you think about it, every single transaction, because of serialization, all other transactions from the perspective of this one transaction happen before it or after it. Beautiful engineering. Now we move to these distributed systems, and it's like Einstein's universe. My perception of time and your perception of time is different, right? My microservice is running at one speed and doing things at one time. This other microservice is doing something at another time. And we're going into this bizarro kind of, trying to wrap your head around, time, Newton's universe, which is very different than a more intuitive, Einstein's universe than the more intuitive Newton's universe. So Akka has an implementation of event sourcing and CQRS built into it. It's called the boring name. It has Akka persistence and Akka persistence query, and it also uses cluster sharding. The result is that, I'm not going to get into details here, but just really quick, there's actors that represent the entity, like a bank account. There's an actor for each active bank account. So my bank account and your bank account, if we're both interacting with this system right now, there's an actor around that has the current state, like our current balance. That's the aggregate. It's aggregating all the deposits and withdrawals and has the current balance. But what's happening is commands are passing through it, events are being emitted and written to the event log, and then the entity, say for example the bank account, is updating itself. At the same time, these events are being pulled over from the event log onto the query side, right? All built into Akka. So people that are using Akka persistence and Akka persistence query, this is what you're getting. You're getting event sourcing and CQRS, where we're considering these things like message propagation, right? It's a pull. It's at least one guarantee of getting messages, the events in the event log over to the read side. What this results in is that Akka is kind of for our stuff, and this isn't the only approach. You can do event sourcing and CQRS with other technologies, but I'm kind of getting into some of our stuff. With Akka, we already have the ability to run in a cluster, so we're kind of eliminating single points of failure. You can run in one node, but you can run on n nodes, and it's Akka persistence running across all those nodes. It's already built to handle running in a cluster, and these are individual services. Right, so you can use Akka and Akka HTTP for the endpoints. You could use Akka and Play, and Logom is a microservice that's built to do event sourcing and CQRS. And all the things that I've been talking about in dealing with guaranteeing message delivery between the write side and the read side is built into Logom. Even guaranteeing that messages coming from the event log into a topic, into Kafka, it's got the at least once delivery mechanism built into it. It's already baked into Logom, all these things I've been talking about. So the result is that you have now kind of a double level of resilience here in a way. You've got clusters within clusters. And what I mean by that is that you've got a cluster of microservices, and the nice thing about a microservice system is that you lose a microservice, but the rest of the system compensates for it. The system as a whole keeps running. The one example that I like in Netflix, I hear this over and over. Say in Netflix, part of the UI is showing recommendations of movies based on who you are. But say that service is down. Netflix keeps working, and you just see a subtle change on the UI. You just don't see recommendations based on you. There might be default recommendations, right? There's some compensating action. So the system as a whole, from the perspective of the users, is still functioning. But behind the scenes, things are broken, and it keeps running. We take it a little bit step further when you can build a microservice that can run, say, as a cluster. And basically, the fundamental technology here is Akka, right? Doing things like Akka persistence, where the service itself can take a hit, but the service keeps working, instead of the service itself going down. So I'm almost done. The last thing I wanted to cover here is probably, especially if anybody a data architect in here? Okay, good. Was there one? Anyways, this one is a little hard for some people to deal with, but what the scenario here is that, say there's these three services, and there's a customer service. So every change to a customer happens in this customer service. But now we have this reliable message delivery system that we're not going to drop any messages. That opens up the opportunity for things like the order service and maybe the shipping service. Every time a customer change occurs, they're subscribing to those events. They hear those events, and they record information about customers in their own schema. The idea here is that now it's a form of optimization and a form of resilience, in that instead of order having to reach across the customer every time it wants to get customer information, which is over the network, right, and pull some customer information, it's got customer information readily available in its own database. So that's a form of optimization. It's also a form of resilience because order can continue to function when customer's not available. Customer could be down, the network between order and customer could be down, so order can continue to function. This is a technique that some of that a lot of people are starting to think about. I've heard other talks where this has been brought up. I think it's brilliant because it gives you that loose coupling, right? That autonomy in your services. So finally, we're here. It's 2017, almost the end of 2017. This is a recent graph. I think it was from IDC, a study done by IDC. It's a projection of the increase in the amount of data between now and 2025. And I think this is actually a conservative curve. I've seen other curves that go almost start to go straight up, not too far off. So some of you guys probably are already running into this. You got systems where you're dealing with massive amounts of data, but the rest of us, I think, we're going to be running into this, that it's not going to be too long before we're going to be processing vast amounts of data, like the big wave of IoT. And when the data scientists and the business realize that you don't need to throw away data anymore, they're going to be beating you going, hey, stop doing CRUD. Save the history. And we want all that data. We want to mine that data and do machine learning and AI and all the other crazy stuff that people want to do with their data. Don't throw away data anymore. I think it's going to go way up. As a result, we're going to have to build systems that can really handle these kinds of loads and do it well. So it kind of comes back to, reactive, right? Elastic and resilience. I'm all about resilience. I love building systems, and this is why I fell in love with Akka. I was finally able to build a system that could take a hit and keep running. Finally. I was sick and tired of I was a developer, I was an architect, but when our systems went down, I was on the phone for 20 hours, trying to help get the system back up. On the weekend when my family was yelling at me for not being with them. That's not a fun place to be. It's really fun to build resilient systems that can stand up to that simian army. So that's what I have. Thank you very much. Any questions? Yeah, you're right. And it's not something, it's not across the board, right? So it's not a case in all situations. And there's also privacy, right? That some data you can only keep for a certain amount of time. So you can't keep history forever. So it's not a solution for every single thing. The point I wanted to push it though, because it's like, it's almost like flip it. Think about trying to keep all the data as long as possible instead of throwing it away automatically, right? And compromise when you have to do it. And the other thing I think will be kind of surprising, especially like orders. I've asked some people that are doing event sourcing in CQRS, it's like how many events actually contribute to the state of an entity? And it depends very much on the application, but in some cases it's like 5, right? So you got 5 records instead of 1. And they're usually probably 5 fairly tight records, right? It probably results in more data that you actually physically have to store, but not a lot, right? It's not like a huge thing. On the other hand, a bank account, you have kind of a never-ending history, right, for perpetuity. But accountants don't use erasers, so it really depends on the situation. So your point is dead on that you just don't go out and say, yeah, we're going to keep every single piece of data. But I think it's reverse the thought process. Assume you're going to keep it until you have justifiable reasons not to, not just assume you're going to get rid of it.
Yeah, I think each different message type would have to be evaluated.
Exactly.
In the case that every single request actually,
yes.
For this use case, less.
Right, and like even an order, it might be that over time it's uninteresting to keep add item, remove item, but it's more interesting to know when orders were created. And and who did it.